Welcome to Study Loop.
So the given question has two parts. The first part is that we have to show that the boundary value problem y double dash plus lambda y is equals to 0, which with the conditions y0 is equals to 0 and yl is equals to 0 as only the trivial solution for the cases lambda equals to 0 and lambda less than 0, right? So first we will write the auxiliary equation r square plus lambda is equals to 0, right? So we get the roots as r1 is equals to under root minus lambda and r2 is equals to under root minus lambda, right? So let's suppose lambda is less than 0, so minus lambda will be greater than 0, right? So the roots will be the real roots and distinct roots. So we have the general form of the solution as c1 e to the power under root minus lambda x plus c2 e to the power minus under root minus lambda x. So the first condition which we have is y0 is equals to 0. So we have c1 plus c2, right? So we get c2 equals to minus c1. Now from the second boundary condition we have yl is equals to 0. So we have c1 e to the power minus lambda l plus c2 e to the power minus under root minus lambda l. Since c2 is equals to minus c1, so we can take common c1. We will get e to the power under root minus lambda l minus e to the power minus under root minus lambda l. So from this equation we get since there can be either two possibilities, either c1 is 0 or this term is 0. Since this term cannot be 0, so we have c1 is equals to 0, which gives the value of c1 is also equals to 0, right? So the only solution to the boundary value problem is y is equals to 0, right? Now in the second case, if we have lambda is equals to 0, right? So we have the equation as y double dash equals to 0, which if we integrate twice, so we get, after integrating twice, we get c1x plus c2. From the boundary conditions we have that yx has two zeros on the interval 0 to l. However, yx is a first degree polynomial, so it can have at most one 0. This implies that yx is equals to 0 for all the x, which is what we wanted to show, right? Now we'll go to the second part. The second part says that we have to show that for lambda greater than 0, we have to find the values of lambda for which the problem has a non-trivial solution and give the corresponding solution, right? So for the second part, we'll plug the y l is equals to 0, right? After putting the value of c1 equals to 0, we get y is equals to c2 sine under root lambda x, right? Because since lambda is greater than 0, so it is having imaginary roots. For the imaginary roots we have the general solution, right? So we get 0 equals to c2 sine under root lambda l, right? So from here we get sine under root lambda l is equals to 0. It can be 0 if sine n pi. So after comparing we get n pi is equals to under root l, under root lambda l, or we can say the value of lambda is n square pi square divided by l square, right? Therefore we have the solution as y equals to c2 sine n square pi square by l square x, right? So therefore y equals to c2 sine n pi by l, sorry, under root, right, n pi by lx. Therefore lambda equals to n square pi square by l square, where n is a positive integer, right. For these values we have non-trivial solutions, and the solution is y equals to c2 sine n pi by l x, right. So this is the final answer for the given question.